So yeah, my name is Kelton Halbert. I'm from the University of Wisconsin-Madison, working in the Cooperative Institute for Meteorological Satellite Studies, which I don't do anything satellite related, so it's a fun thing. But I'm here on behalf of my advisor and PI, Dr. Lee Orff, to talk about what we use Blue Waters for, and that's simulating violent, long-lived tornadoes using numerical models, and have some new and interesting stuff to show from that over the last couple months, actually. But first off, just the problem of what we're trying to use Blue Waters to solve is that supercell thunderstorms tend to be responsible for the strongest and deadliest tornadoes in the EF4 to EF5 damage rating range, which again are responsible for the largest losses to life and property. But we don't fully understand why these storms develop, as they're only a small subset of all tornadoes, and even at that, all supercells. Only 1% of tornadoes are classified as violent, and of that, only a quarter of supercells approximately produce tornadoes. So it's a very difficult prediction problem, and made even worse by the fact that we actually don't even understand the dynamics that lead to tornado formation in general, much less the deadliest, most costly ones. On top of that, collecting observations from supercells and tornadoes is incredibly challenging, often very dangerous, and the resolution, either spatially or temporally, can often be too coarse to get at some of the underlying processes that lead to tornado genesis and maintenance. And so that's where the numerical modeling comes in, is that by using the full set of fluid dynamic equations and providing sufficient resolution, that we could maybe get at the processes in these deadly tornadoes and maybe start to distinguish them from the not so deadly tornadoes and lead to better prediction. So kind of going off some of that again, the reason why people care about this is right now the tornado warning false alarm rate is about 70% for the National Weather Service, and that's been steadily decreasing over the last several decades, but that's still a high false alarm rate if you want people to actually take you pretty seriously. And on top of that, there are still rare situations in which tornadoes occur without warning. This is much less the case these days, but it can still happen and still can be even a deadly or violent tornado with no warning. And we want to eliminate that, give people as much heads up as possible. Again, more fatalities in the rarer events, and so people care about that. And despite the advances in numerical modeling and operational meteorology, we weren't really able to get the resolution required to get at some of these processes until Blue Waters. And that's what my advisor started doing when the first allocation in 2013 was to start working on these problems. And so to do these simulations, we've kind of had to, in conjunction with some of the Blue Water staff, come up with some creative ways to handle things like the data load. We realized that with wanting to save these high-resolution data sets, both temporally and spatially, we didn't need the full range of 32-bit or 64-bit precision, so we used the ZFP plugin for HDF5 to provide an accuracy parameter that then for each array, and we can decide how much of one thing we want to compress and save versus another. And that's really allowed us to actually run these things at scale and save the data and do proper analysis. On top of the data storage was the model I/O problem. So Lee had to rewrite the entire model's I/O core to effectively work as a distributed file system. He calls LOFS, or lack of file system. And it's just a bunch of HDF5 tiles that are self-describing that can then be reconstructed on request after the fact. And that means that when the model's running, it's spending less time communicating arrays to MPI and allows it to just write and move on to the next step. In order to save space, we only save the bare minimum fields, which means that we use a lot of GPU code to recompute necessary variables post hoc. And same thing, we've started to develop trajectory, Lagrangian trajectory code on the GPUs on Blue Waters that will allow us to do more complex quantitative analysis with some of that stuff. So these are just some of the challenges we've had to go through, and beyond just running the simulation and actually taking advantage of Blue Waters to its fullest. So previous work that some of you might be familiar with from previous years was Lee's process was kind of setting up the model. In 2013, there was a successful simulation of an EF5 tornado at 30-meter resolution. This has kind of been our control run that we've been working on since I started at Madison 2 years ago. That data set's about 67 terabytes, contains 32,400 times saved every model time step, which is 1/6 of a second, throughout the entire life of the tornado. So we basically saved the entire simulation in Amber so that we can do all the visualization and analysis we want without having to rerun on the nodes. And it's kind of nice that way, and that's where the GPUs are super helpful. We've also done simulations of the same environment at 20 and 15 meters, and then some new simulations of different supercell environments that have produced other violent tornadoes and some different storm structures. So we're starting to see some patterns in other atmospheric environments that show these things might actually be real, and starting to uncover that. And so to the fun stuff with the animations, this is a sequence put together by David Bach at NCSA. It's one of my favorites because when people ask what I do, I just kind of show them this and go, that's essentially it. But in more detail, the simulation is essentially initialized from a virtual weather balloon profile that gives us temperature, dew point, pressure, and the winds. And we put that in a horizontally homogeneous base state in the model, and we perturb it with a little updraft, and we say run. And so this is what the model ends up doing, is it grows a thunderstorm in that environment, and then we essentially hope and pray that it produces a tornado. We actually don't know going into it whether or not you get something that looks as good as that, or if the whole thing kind of just blows up into a convective mess, or if it's a supercell without a tornado. It's very random. That's the process of how we grow it. And then through these simulations on blue waters, we've identified some new features previously not talked about within the sciences. This is something we call the streamwise vorticity current that we believe to be very important for either both tornado genesis or maintaining strong, long-lived tornadoes. And it's actually a feature that has motivated several field projects. There's actually one ongoing right now based on this work to go and hunt for these features in supercell thunderstorms. And talking to a couple colleagues, they've actually managed to find them in reality. And it all started with some blue water simulations. This is just another view of a similar thing with the vorticity field, or the amount of spin and rotation. And again, just picking up on the fact that there are these really small, fine-scale features that seem to be important that we just miss if we look at things in the traditional observation networks with radars, or even the 100-meter simulations of previous studies that deemed those to be sufficient resolution. We're finding that there's even smaller scale features that are important. A lot of what we do is also comparing them to observations. And so this is something put together by a storm videographer named Hank Scheima from Houston, and essentially putting side by side the simulations with the real atmosphere. Is the model actually showing us things that we know to be true? So when you've got something this high resolution, you're seeing features that haven't been seen before, you've got to look for other cues that tell you, okay, this is physical or representing real life. I always enjoy looking at this sequence because it really points out how many of the flow features seem to be matching the real atmosphere, and showing that we're probably on the right track with some of these things. And again, it's motivating others in the field to start looking for some of these important features. And it's pretty exciting because of that, and seeing other people find things that you've only seen in a computer. But with that said, I think this is the end of the sequence here, but this was our 30-meter simulation run, which we can now have managed to get scaling on blue waters well enough that we can do these pretty routinely. I think we can chug one of these out per day if we wanted to, or maybe it's 2 days, but pretty quickly, doesn't use that many nodes. The exciting stuff right now is within the last couple months, Dr. Orff has really kicked things up to 11 with the simulation. And so we're working on a new HERO simulation at 10-meter resolution, completely isotropic throughout the whole domain, about 250 billion grid points, 1/20th of a second model time step, and a single restart checkpoint was weighing about 35 terabytes on the disk. So turning on some compression, we were able to make the run go further out and save more of the data that way, but we can't use any lossy compression with the restart checkpoints. We started running it in April. We're only about out to 6,000 seconds of the simulation. I'm not sure how far Lee wants to go with it, but we do finally have an EF5 tornado at this 10-meter resolution. And because of the challenges of the previous simulation that we've kind of worked to overcome, this is more than just kind of a one-and-done visualization. Can we do it? It's actually going to be saved and analyzed at scale as well, which is really exciting. So here's some of the animations from this. Literally just got sent to me yesterday by my advisor. Some really exciting stuff with the 10-meter simulation, but this is the vertical vorticity painted on swaths at the lowest model level. And we can see these really unique features where we're seeing that the tornado genesis and maintenance is kind of more of an aggregation of vortices from all over, and we're starting to see smaller sub-vortex features that match what we see in reality with the damage paths and swaths. And these were flow features that we weren't able to capture in the 30-meter simulation due to the resolution. So now these are actually the sub-tornadic vortices, and again, you can see it in the horizontal wind speed maximum that southern side is kind of being dug out, similar to that photo from the EF4 tornado in Illinois. This one's just showing the pressure minima along the track. So again, we're getting these individual subsuction vortices within the tornado. And that's really important because these multiple vortex tornadoes that have these small suction vortices can actually have translation velocities that are near 200 miles per hour, not including the rotational component. So understanding the dynamics of those is of great interest to the community there. A similar video, but with our buoyancy field, essentially, or whether or not the air is rain-cooled or from the warm inflow. And even at 10 meters, we see a similar result to some of our previous 30-meter work, in that most of the air that feeds the tornado actually comes from the rain-cooled downdraft air, which is something that is pretty interesting, and it seems like all the vorticity that feeds it comes from out there as well. I'm going to see if I can jump ahead a little bit for the sake of time. Cloud field of the simulation at 10 meters, again, just kind of showing the structure of the tornado. It looks pretty realistic. It's kind of mind-blowing to think about that this is a simulation and not real life. Sometimes I did some storm chasing in undergrad, and it looks just about as real of a tornado as any I've seen. And again, just getting those really small, fine tornadic structures is really exciting because nobody's been able to do this with the whole parent supercell involved in the simulation. Again, just from a different view, I think there's a comparison to that same Fairdale, Illinois tornado from that had the swaths in the earlier thing. Yeah, there it is. So again, just making sure that we're capturing the right flow features, and it's doing pretty good. So this is officially the highest resolution simulation of a supercell and tornado ever conducted to date. It's still going right now. So if you see the queue fill up with about 3/4 of the XE nodes, I apologize. It's probably us. Yeah, so this is just again, the vertical vorticity field showing, or volume rendered painted with the magnitude on the surface, just showing we're getting these individual suction vortices within the tornado, which is something that's very new to these simulations for us. And just let that run for a moment as well. And yeah, so just some parting thoughts. Blue Waters has enabled breakthrough science in supercell and tornado modeling. As of now, the 10-meter simulation is the highest resolution study of a supercell and tornado ever conducted. It's still ongoing. I don't have much to say about scientific results of it because of that, but it seems like we have convergence of solutions between our 30-meter and our 10-meter run, which is good. And we have a couple of questions we want to address between the two simulations. But the Blue Water staff was instrumental in getting things like the ZFP compression compiled and set up, handling node failures and reservations with this simulation. I know Lee's been super thankful for how responsive people have been on the Blue Water staff whenever a node goes down or the simulation hangs or the I/O hangs. And then it'll continue to be instrumental as we continue to run this data set and then hopefully move it off quickly enough and can then continue to do analysis further on. And just throwing up the acknowledgement slide for all the collaborators and the NSF grants that support this work. And thank you to Lee for having a talk in Canada so I get to enjoy the beautiful weather in Oregon. And with that, I'll take any questions.